class 11, classification of elements and periodicity in properties. Right? When we're looking at this particular chapter, this is one chapter in which we are going to study the entire properties of elements, the history, how the elements they were arranged, and the scientists who helped to arrange these elements in a tabular form. Right? Now basically what happened was, initially when very few elements they were discovered, then it was very easy to remember them. But later on, as more and more elements they were discovered, the need was felt to arrange those elements in such a manner such that we could make the, you can say, the study of the elements very, very easier for us. Okay, or in other words, we could study the properties of elements effortlessly. Okay, so this was the main objective, to line up all the elements in one particular arrangement, and the scientist who first felt the need, his name was Huxley. Huxley was the first scientist who thought or who brought up that the elements they should be arranged in such a manner so that their properties they can be studied effortlessly. Okay, slowly and slowly, then when more and more elements were coming in and the scientists they were trying to find out a method as to how to arrange these elements, there was one formulation which was given, which was known as the periodic table. Okay, now what do we understand by periodic table? Periodic table, it is the arrangement of elements such that similar elements are placed together and dissimilar elements were separated. This was the main objective, and this was the definition of periodic table. Various experimentation was done, or various theories were given with respect to the fact that how the elements should be arranged pertaining to which particular property of the elements, right? So after the Dalton's atomic theory, when Dalton gave his atomic theory, atomic masses were considered. Atomic masses were considered to arrange the elements in one fixed, or you can say one disciplinary manner. Okay. Now arrangement of this, when we are talking of, we are going to start the chapter with the historical development of the periodic table. Historical development of the periodic table, right? Now initially, as I just told you, very few elements were known. Therefore, the first scientist who tried to arrange these elements, his name was Daubeney, and he gave his law of triads. Triads over here means arranging the elements in group of threes. Okay, so in group of threes, Daubeney arranged the elements in such a manner that the first element, the atomic mass of the center element was the arithmetic mean of the first element and the third element. Okay, so according to Daubeney's triad, the groups was arranged in such a manner that the atomic mass of the center element was the arithmetic mean of the first and the third element. Also, the properties of these three elements, they were almost same, right? So particularly when we are talking of chemical properties, when we are talking of valencies, we will see over here that the valencies and the chemical properties of all the three elements in one triad of Daubigner, it is going to be same, right? As for example, the first triad given was lithium, sodium and potassium. We know that the atomic mass of lithium is 7, the atomic mass of potassium is 39. So when we take the arithmetic mean of both of these, 39 plus 7, that is 46, and 46 divided by 2, that is going to be 23. The atomic mass of sodium was calculated to be 23, which was absolutely accurate. Okay. Then the second one was chlorine, bromine and iodine. The atomic mass of chlorine was 35.5 and that of iodine was 127. The actual mass of bromine given was 80, but according to the law, the arithmetic mean of 127 plus 35.5 divided by 2, this came to 81.25, which was very close to 80. Okay. Then the third triad which was suggested was that of calcium, strontium and barium. The atomic mass of calcium, that is 40, and the atomic mass of barium is 137. Right? The exact mass of strontium, that was 88. But when the arithmetic mean was calculated, that is 137 plus 40 divided by 2, this came to 88.5. So that was also quite close, right? In a similar manner, there was another triad which was given, that was for sulfur, selenium and tellurium. Sulfur, selenium and tellurium, whereas the atomic mass of sulfur, that is 32 and that of tellurium is 127. Okay, so when the actual mass of selenium seen was 79, but the calculated, that was coming to 79.5, which was again very close. Okay, but there were other elements, like for example, when we are talking of iron, cobalt and nickel. Iron, cobalt and nickel was another triad, but Daubigner failed to explain, according to his law, the similarities in all of these because of almost same atomic masses, right? Ferrous, cobalt and nickel, they have almost same atomic masses. Therefore, Daubigner failed to explain the properties or the similarities between these three elements. Okay, so Daubigner's this law was only confined to very few triads, but practically it seemed to fail very soon. Okay, when more elements were given, many elements, they were unable to follow this law. So the next, you can say, the table that was given by Newland. The second table was proposed by Newland and his law was known as Newland law of octaves. Newland law of octaves. Now, according to this law, Newland suggested that the first and the eighth element, he arranged the elements in, you can say, vertical or horizontal, in horizontal rows, in which he said that the first and the eighth element, it bears similarities just as the scales of music. When we are talking of scales of music, so we have sa, re, ga, ma, pa, dha, ni, right? And the eighth element then again comes to sa. So just like the notes of music, he suggested that the elements should be arranged in such manner that the first element and the eighth element should bear similarities in their properties. Okay. So Newland's law of octaves, it was given as what? Like when we're talking of the first one, we have hydrogen. Okay. And then after hydrogen, he placed lithium, beryllium, boron, carbon, nitrogen, oxygen. Okay, and then after that fluorine. So we have, this is the first element, first, second, third, fourth, fifth, sixth, seventh, and the eighth element has similarities to the first one. Right? In a similar manner, we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and then chlorine. Right? And then after chlorine came potassium and calcium. The law only could be explained over here for lighter elements like alkali metals and alkaline earth metals, and also certain non-metals which had less masses. But when the atomic masses increased, that is for heavy metals, this law was given a blow. Like it could not explain, he placed chromium over here, which had no similarities with aluminium. Right? In a similar manner, titanium was placed here, manganese was placed here, and iron was placed here. Now these were the anomalous behaviors because chromium has no similarities with boron and aluminium, titanium has no similarities with carbon and silicon, manganese has no similarities with nitrogen and phosphorus, and similarly iron has no similarities with oxygen and sulfur. Okay? So because of this, Newland's law of octaves worked quite well for lighter elements, but when we went to higher elements, this law was overruled very soon. Right? Then the main idea or the main work regarding the periodic table was first of all given by Lothar-Meyer. Basically, Lothar-Meyer and another scientist, Lothar-Meyer was a German scientist, okay, and there was another scientist, Mendeleev, who was a Russian scientist. They were independently working on the periodic table in different parts of the world. Okay, now when we are talking of Lothar-Meyer's arrangement, the distinction between the two is that Lothar-Meyer, he was working more on the physical trends of the periodic table or physical properties of the elements, whereas Mendeleev, he was working more on the chemical properties. Right? Although for both the main objective was to arrange the elements in order of increasing atomic masses. Another distinction was that Lothar-Meyer proposed his table graphically. Depending upon the physical properties of elements. Like for example, he calculated the atomic volumes of various elements by the formula atomic mass upon density. Right? So depending upon this, he gave a graphical representation to us, plotting the graph between atomic volume of the elements with that of the atomic masses. So let's have a look at his graph. He plotted a graph between atomic volumes and atomic masses. The graph was having a maxima, a minima, right, and also certain plateau regions in the center. So let's see, his graph looks something like this. So this is the maxima, then a minima came, and then again another maxima, right? And for this there is minima over here is a plateau, and then another maxima, and then again a plateau, and other maxima, right? So what were the elements which were placed at the maximum peaks which we can see over here? The first element which was placed over here, this was iodine, okay, and then was the peaks were all occupied by the alkali metals, sodium, potassium, rubidium and cesium, okay, and then we had at these points, this is aluminium, this point was carbon, and in the plateau which we can see first were the heavy metals like vanadium and cobalt, okay, and then was alkaline earth metals which were present at the descending peak, okay. So this is magnesium over here, calcium over here, and in a similar manner we have selenium. Then the plateau will again contain the heavy metals like niobium, molybdenum and zirconium, right? And then we have tellurium over here and cesium there, and then we had barium over here, strontium over here, okay, and then over here was lanthanum. Now what did this arrangement suggest? He suggested that all the elements which are at similar positions in the graph, they had similar properties. Like for example, when we are talking of the alkali metals, sodium is at the peak, then after that potassium is at the peak, rubidium is at the peak, and cesium is also at the peak. So all these sodium, potassium, rubidium and cesium, they had similar properties, right? In a similar manner, you can see over here that magnesium is over here at the descending peak, right? Similarly, calcium is at the descending peak, strontium is at the descending peak, and barium is also at the descending peak. So all these, they will also have similar properties. Clear? And the heavy metals, they are placed at the minima where plateau is present. So vanadium, cobalt, niobium, zirconium, molybdenum, all these, they are heavy metals. So this graph gave us a good idea about the physical properties, but it could not give us any idea how the chemical properties of the similar elements, they were associated with each other. Okay? So this Lothamier's arrangement, it was, you can say, it failed on the observations that physical properties of elements, they are a periodic function of atomic masses. This is what he stated, that the physical properties are a periodic function of atomic masses, right? This was the statement which was given by Lothamer. To give it a better form in which we can easily understand all the properties, the next tabular form of this arrangement, the same idea which was used to give us the tabular form, that was given by Mendeleev. In fact, we are going to study two different periodic tables of Mendeleev. Today we will study the original table which he had given, And then after that, there were certain modernizations done on the Mendeleev's table, and then we have another table which is known as the modern Mendeleev's table, which we will do tomorrow. Okay, so let's go on to Mendeleev's original periodic table. Mendeleev's periodic table. As I just told you that Mendeleev also used atomic masses, right? And he said that the chemical properties are a function of chemical properties of elements are a function of their atomic masses. Right? So chemical properties are a function of their atomic masses. This was Mendeleev's periodic law. Okay? Now according to this law, the elements, they were arranged in order of increasing atomic masses. Okay? Now his law was proposed in the form of a, as I just told you, it was proposed in the form of a table. Okay? Now when the table was designed, there were certain points which were seen according to his table, which was known as the postulates of Mendeleev's periodic law. So you can write down these postulates. Number one, the elements if arranged according to their atomic weights, if arranged according to their atomic weights, exhibit periodicity in properties. What is periodicity in properties? Basically, periodicity is the recurrence of similar properties after similar interval of times. Okay, so that is what periodicity in properties is. Then number two, elements which are similar with respect to their chemical properties, may either have same masses, like iron, cobalt or nickel, or the masses may increase gradually, like in potassium, rubidium and cesium. Number three, the arrangement of elements or groups of elements in order of their atomic weights correspond to their valencies as well as their properties. Number four, the magnitude of atomic weights. Then number five, many yet unknown elements may be discovered. So during the Mendeleev's periodic table, there were many elements which were not discovered. So Mendeleev kept those places empty, suggesting that there were many elements which were yet to be discovered and could be placed in those particular spaces. Okay, and then number 6, certain characteristic property of elements, certain characteristic properties of elements may be foretold from their atomic weights. Without doing any experimentation or without doing any, you can say, any, what else can you say, what else word can you use, without doing any effort, according to which he could explain the properties without doing any effort, he suggested that only by knowing the atomic weights, the properties of the atom can be, or the element can be very well manipulated. Okay? Now there were, what he did was, he basically arranged all the elements in tabular form, in which they were elements of similar properties. They were placed in vertical groups. They were placed in vertical groups, right? So similar properties, they were present in vertical columns, and the horizontal rows they were known as periods. Horizontal rows were known as periods, right? So basically he laid emphasis on the fact that all elements with similar properties, they should be placed in similar groups, and all those with dissimilar properties, they should be placed in different groups. This was the main objective of the table. Okay. Then there was another very important thing over here, was that he was so confident about his table that he kept certain empty spaces for unknown elements which were not discovered. For example, he kept places for aluminium. Means after, right? And gave certain properties to this unknown element which was not yet discovered, and this element was gallium. Later on, it was seen that gallium fitted very well into the space which was kept by Mendeleev, and secondly, it had the same properties as predicted by Mendeleev. Okay, then another one was silicon. Again, means after. Silicon, which had the same properties as germanium. Which had the same properties of germanium, right? So these, germanium. So these were places which were kept empty by Mendeleev, and the elements gallium and germanium, they were discovered much later, but they had similar properties as predicted by Mendeleev. Okay, and then elements, the original periodic table which was given over here, that consisted of 8 columns. Right? They consisted of 8 columns or vertical groups, which were vertical columns which were known as groups. Right? Each group had elements consisting of similar properties. But this table consisted of many, you can say, defects. For example, in this case, the position of isotopes it was not explained properly where to place the isotopes, and then anomalous pairs were kept together. This we will discuss in detail in our next section when we are going to do the limitations of Mendeleev's periodic table. Anomalous pairs. Anomalous pairs means that the elements having difference in properties, they were kept together, right? Whereas there were certain pairs which have similar properties, they were kept separately. Then it also could not explain the position of lanthanoids and actinoids. Okay, so today we are going to do only till here. At the end of this, the periodic table of Mendeleev, that is shown as coming up, right? So the Mendeleev's periodic table, the original periodic table looks something like this. You can see at the figure over here, and also it is given in your notes. Okay, clear?